Welcome to lecture 4 of section 2. We are going to pick up where we left off, looking at perception of auditory signals. We spoke about the receptors and then the thalamus. In the thalamus, we mentioned a specific nuclei that plays a role in auditory processing, and that is the medial geniculate nuclei. And from there, the information gets projected or sent to the primary auditory cortex, which is located in your temporal lobe. Once the information arrives, this darker pink area here is the primary area, and then the secondary area is surrounding it. Once it goes through those two pathways of being interpreted and bringing meaning to the vibration, the action potentials from the vibrations, the information is sent in two directions. One goes anterior, which helps us identifying what the sound is. It goes to the prefrontal cortex and the frontal lobe to help us process what it is we're actually hearing. And then the other pathway is the posterior auditory pathway. And what it does is it actually sends the information back to the parietal lobe. Think about parietal lobe. What is its job? Its primary is somatosensory, which is placing yourself within your environment. That kind of makes sense that that's where the sound information would go if you're trying to help process all of the information that's incoming. If you think about it, all of these senses are sending information at the same time. It's not a one-for-one. You're not only seeing something, you are seeing, hearing, and feeling an environment. The association cortex is extremely important. It's where all the information starts to collide. Where does the occipital lobe? It's in the back, right? It sits back here. And you remember there were two pathways that were projecting from it for the association cortex. One was where? It was dorsal, and it went to the parietal lobe. So information from your vision and from your hearing are both going to the parietal lobe to be processed. And involved and included with all the other information coming in from your senses, from your touch, which we haven't gotten to, we'll get there. And it also sends information ventrally, the occipital, the visual pathway, to your temporal lobe, and that's to help you identify what the object is that you're seeing. Interesting, isn't it? So these pathways are all converging upon each other. Again, this is a place where you need to look at, compare and contrast between the two systems. Because the visual, it's dorsal and ventral. Auditory, it's anterior and posterior. So that brings us to the end of auditory sensation and perception. What we're going to go into now is talking about additional responsibilities that the ears have that's not part of hearing. Yes, our ears and our cochlear and all the pieces of our inner ear play a critical role in helping keep us stable and balanced. This is called the vestibular system. So the vestibular organs are important to helping our body understand where it is in regard to the major force that it always feels, which is gravity. Gravity is what keeps us on the planet, and everything we orient ourselves toward is that sensation. This is why like roller coasters and those types of things are fun, because it throws those things off and it forces our bodies in directions that it's not used to, which is why it's exciting. The vestibular organs also help us understand the change in direction and speed of our head. So when I was a child, I loved spinny rides, tilt-a-whirls, the scrambler, all of those fun things. Now I can't stand them. If I go on them, I get a headache, I get nauseous, and I'm miserable the rest of the day. And so therefore, my vestibular system has become more sensitive to that rotational spin. And it doesn't like it, and it makes me feel like garbage for the rest of the day. So I don't ride them anymore. But again, that's the system that we're talking about. So it involves the three semilunar circular canals, which is in the cochlea. And it involves specific organs called the otolith, which has the uticle and the saccule. Go watch this race if you've ever been to a minor league baseball game. I don't know if they do it at major leagues because I haven't been to one in a long time, but they have people spin around a bat, right? That's what this is a video of. So you can see how the molecules get spinning in the brain and how our brain, when we stop spinning, continues to want to do that because that's what the organs are detecting inside of our ears, that we're still doing that because it's in fluid. So it takes a while for it to stop. And that's what you see in that video. We're going to put it into words here, but basically what happens is there's fluid in the semicircular canals that pushes against hair cells. The hair cells are receptors for helping the body understand where it's at, and it provides direction in which way they're being bent. And it has to do with, depending on which way it goes, it's either depolarized or hyperpolarized. But that sensation is feedback that's coming to the body. to the brain. Here's what we're talking about. These semicircular canals here, which are off of the cochlear. These two organs right here are responsible for detecting this action within regards to gravity. And it's using depolarization, hyperpolarization to send those messages. So unical and the sacral have the hair cells inside them that are designed to detect these calcium carbonate crystals called otoconia, which are, when they touch the hair cells, it's going to change the way in which the action potentials are being sent. And that's the sensation that's picking up. So it's not the vibrations and picking up hearing. These hair cells are focused on being able to identify these calcium carbonate molecules and send information via the vestibular nerve to help the brain orient itself or understand the changes in orientation that are occurring. Beyond that, let's apply what hearing does and what are the connections that we have to music and language. We've already used them as examples. You can't get away from that when we're talking about hearing. But now we're going to go a little bit more in depth about the actual processing of language and music in the brain. Obviously, sound waves have to be present for us to hear anything. Music creates sound waves, language creates sound waves. And one of the pieces that our brains do, or what happens as we develop, is we train the brain. The brain is trained into recognizing the importance of verbal patterns and what sounds to actually pay attention to. So there are two major areas associated with speaking and language. Broca's area is responsible, and it primarily is in the left hemisphere, but it's on both sides. But the left side is primarily responsible for the interactions with the motor cortex. So this is located in the frontal lobe, and it's where our frontal lobe drives movement, and it helps us produce the movements of our mouth, of our tongue, of our teeth, our jaw, all of that to create words. Wernicke's area is actually in the temporal lobe. And again, we focus this on the left side because there is lateralization of the brain, and we'll talk about that in a moment. It's in the rear part, and it actually helps us regulate and understand and tease apart what language we're hearing and the comprehension and the meaning behind the words. So Wernicke's critical for hearing and comprehension, while Broca's is very important for speaking. And our brain is lateralized, and we'll get more into this when we talk in section 3 about the lateralization of the brain. Music is primarily processed in the right hemisphere. The right hemisphere is known for picking up patterns and looking at the kind of global bigger picture. Now, the left side is responsible for analyzing and helping us understand language. Language is a more detailed, nuanced process of understanding the environment. So left side, detailed language. Music, pattern, right side. So you can kind of keep those separate. But again, Broca's and Wernicke's area are on both sides of the brain. However, the left side, because they're so connected to language, either comprehension and or movement, the creation of language, they're located on, we focus on the left side when we're studying it. All right, so what area right here, what am I showing you a picture of? You have the primary auditory cortex, and then you have it move into this outer area, it's temporal lobe, and it's helping us comprehend the words we just heard. You said Wernicke's, you're right. So here's a more complicated look at what's happening. So again, we're looking at the left side of the brain. The information comes into the primary area, goes into the second area, which Wernicke's falls into. When it is hearing and comprehending, it's starting to send information to the frontal lobe so that we can actually create a response. Not only do we have to think about the words we want to say in our cognitive response, but we also have to think about how do we make those words come out of our mouth. Luckily, most of us taking this class have no issue with, if we want to say the word hi, being able to say it. We don't have to think about how to make the H sound and how to make the I sound. At one point in your life, you had to. And then Broca's talks to the motor area, which is in the most posterior part of the frontal lobe, and then that sends information down the spinal cords to the cranial nerves to control our mouth and jaw and tongue. Here you have examples of activation in the brain dependent on the type of noise a person's hearing. You hear loud noise, that immediately is going right to the primary auditory cortex. It doesn't go much beyond that because it can process loud noise. When you're listening to words, however, though, it spreads out and it becomes more active and it goes into Wernicke's area. And then when you're discriminating speech sounds, meaning trying to create them, discriminating them, you have activation of Broca's area. Language is a unique thing, and I like to talk about it because all human populations have language. We've created a way in which to communicate. Other species, non-humans, particularly non-human primates, smart mammals like whales and dolphins, have ways to communicate. Human language is something that is universal. However, it has to be trained. Early in life, if you are raised without a spoken language, you will have a difficult time learning that language. You remember if you watch any of those videos where individuals were raised in isolation, they really only had the ability to grunt and create other intelligible noises, things that didn't make sense to us because they weren't trained. They didn't understand. They weren't taught how to speak. So language is not an innate thing. We don't come out speaking, right? We come out with the ability to develop it if we're in the right environment. The most sensitive period to learning a language is roughly from ages 1 to 6 in development. The language area, learning area becomes more solidified and stabilized by age 12. For those of you who are not in a bilingual home, think about, so this would be people who are monolingual, when was the first time you started taking a foreign language? For me, it was high school. So I was 13, 14, which is past the ideal window of learning a new language. And we wonder why it's hard to pick up languages because we don't start them at a young age. Ideally, you would start immersing children in a foreign language early on in their development. Even if they don't master it as a full-on language, if they hear it and they learn pieces of it, they're laying the groundwork so that at some point, if they want to come back and activate that area and develop it, it's at least there. The other thing about languages is that they often have similar structural elements, like a subject, a verb, sentence kind of thing. I mean, yes, you put the adjective before or after, and there's some little differences in grammar and in the order in which you put the words together, but they're all pretty similar with regards to structure, which is kind of cool. Human experience is pretty similar across all cultures. Now, there are times when there are strokes or other type of lesions that can develop, drug use, blunt force trauma, that kind of stuff, where there is damage to different areas of the brain, which actually create problems for the individual to either create the ability to speak or to comprehend the language the things that are being communicated to them. So there's Broca's aphasia. Broca, remember, is responsible for being able to create movements and vocalize information. Therefore, if you have Broca's aphasia, you have an inability to speak fluently or inability to completely convey your ideas. You can hear, you can comprehend, and you have vocal cords. All of that's present and working. It's just this directions of being able to create your response has been dissipated. Wernicke's aphasia is an inability to understand or produce meaningful language, even though they can speak. The area that's affected there, obviously, is Wernicke's, which is responsible for comprehension and creation of responses. And again, I mentioned music is highly processed on the right side of the brain. However, if you create music, play an instrument, sing, that type of thing, when you are playing the instrument, when you are identifying the notes, when you are identifying the rhythm, when you are doing aspects of processing music to make it, that does rely on the left side. So music creation utilizes the whole brain. Just listening to music, primarily you just light is just the right side of the brain. Again, we've got the right side of the brain here that they're showing you. There's a couple different areas that are important for hearing music and that seem to light up. So when you have a burst of noise, again, this is that primary association cortex of the temporal lobe. When you pick up patterns or hear melodies, it's activating the secondary area on the right side. And when you start comparing pitches and identifying appropriate frequencies in the notes, that starts to involve the frontal lobe, which is pulling in more information than just the sound. And you're starting association pieces. So like language, the ability to create music or be musical or prefer patterns appears to be innate, but it needs to be developed. If you've never taught to develop a rhythm in the way you speak or the way you dance or the whatever, if you don't have that given to you or in your environment, you're not going to develop it very easily. However, they do show that infants, when they play music or play notes to the infants will show a preference for musical notes that seem to be as a scale or have some type of pattern versus ones that are just randomly given out. So it seems that music and preference for organized music is something that we do come with an innate ability with. And any point in your development, whether you're a child or adult, individuals often can pick out musical errors very easily. So we seem to have a bias towards rhythms when we're hearing and speaking. This information concludes the end of chapter 10, and now we'll move into somatosensory.
Hi gang, so this is Dr. West, and this is the end of the materials that you will need for this quiz. But I wanted to end this lecture with a video that I found about some really cool new research about music and the brain. It's actually even more complex than Dr. Bennett explained here. Now, again, the stuff that you're going to see in this video is not going to be on the exam. You can rely still on the study guide and on the things that Dr. Bennett explained. But I just thought you would find this super fascinating, or at least hopefully you will. I did. So I thought you might enjoy. Talk to you soon. Bye.
These days, we hear music all the time. It wakes us up, motivates our workouts, keeps us company on our commutes. It doesn't matter what kind of music it is. Music itself has the ability to affect our moods and our bodies in all sorts of ways. We nod our heads, we sway, we dance. Music can give us chills, even make us cry.
Music activates every area of the brain that we have so far mapped. In fact, there's no area of the brain that we know about that music doesn't touch in some way.
But what's behind all that? What exactly does music do to us?
To find out, I went through a whole series of tests designed to measure my responses to music. I met some kids whose brains may actually be changing thanks to those hours of learning, practice, and performing. Spoke with a therapist who used music to help former Congresswoman Gabrielle Giffords learn to speak again, and got a glimpse inside the brain of a 2-time Grammy-winning artist while he played. All to find out how music affects us. So what's going on when we listen to music? We visited the USC Brain and Creativity Institute, where I had my head examined, literally, to try to figure it out.
I'm going to go into this fMRI machine. A tiny tube will surround me. We'll get a baseline reading of my brain, and then I'm going to listen to some music, and we're going to see how my brain responds.
Just close your eyes, relax, and try and get into the music as best you can, okay?
And here's what we saw. These are scans of my brain. The areas in red are where my activity is above average, in blue below average. And as you can see, there's red activity all over my brain, not just in one specific area.
25 years ago, the idea was that language is in the left side of the brain and music is in the right side of the brain. But now that we've got better quality tools, higher resolution neuroimaging and better experimental methods, we've discovered that's not at all right.
How does that play out in different regions of the brain?
When music enters and then gets shuttled off to different parts of the brain, it stops at specialized processing units in auditory cortex. They track loudness and pitch and rhythm and timbre and things like that. There's visual cortex activation when you're reading music as a musician or watching music. Motor cortex when you're tapping your feet, snapping your fingers, clapping your hands. The cerebellum, which mediates the emotional responses. The memory system in the hippocampus, hearing a familiar passage, finding it somewhere in your memory banks. Music is going on in both halves of the brain, the left and the right, the front and the back, the inside and the outside.
So what about a musician's brain?
To play a piece of music engages so many things: motor systems, timing systems, memory systems, hearing systems. There's all sorts of kind of brain activity happening. It's a very robust thing to play music.
Jacob Robertson. I'm Nathan Glenn Robertson.
We asked these 11-year-old musicians to tell us what's going through their minds when they play.
Some of the most important things are having good postures, getting the note right, legato, staccato. For the violin, you need to hold your hand at the right place, and you need to be in tune, and then you also have to have not only the right intonation but the right sound, and then you also need to have great vibrato. There's a lot of things to think about.
Back at USC, researchers have been studying kids who play music over the past 5 years to see how it affects their development. The multitasking areas of their brains understandably lit up, but they've seen other results too.
Music training over the course of 5 years has had benefits in cognitive skills and decision-making, also had some benefits in prosocial behavior, and we've also seen changes in the associated brain structures.
Did you hear that? Changes in brain structures. They found that the brains of children who have studied music have stronger connections between the right and left hemispheres, and that can make them better, more creative problem solvers. And then there's emotion. piece like this, it's easy to understand why emotions play such a big part in music. This song, by Camille Saint-Saëns, is known as the music for the dying swan in ballet. And while it might move ballerinas to dance, it inspires different reactions in others. Some people get goosebumps, the chills, that weird tingly sensation that you get when a great piece of music just hits you in the right way. It's called frisson, and not everyone gets it. But it turns out I do.
Now we're going to have you listen to some pieces of music.
Okay.
When you experience a chill, if you do, I want you to just press the space bar so we have an indication of when the sort of peak moments of enjoyment are happening. Okay.
Matt Sachs, a PhD candidate at USC, wired me up to measure my physiological response.
So when I'm feeling that kind of emotional connection that has a physical manifestation, we'll see what my body is actually doing.
Exactly. All right, how was that?
That had a lot of them.
We got them all.
Now, full disclosure, back in the day, I played the cello, which might have something to do with why that particular song affected me. Nice hair. But it turns out the brain is at work here too.
We process the difference between this pathway that connects the auditory regions, is on the side of the brain here, to the emotional regions, and we show that the tract actually that connects those two regions is stronger, there's more fibers in that region in the people who get chills.
Which means some people's brains might have better communication between what they hear and how they feel. The music itself also plays a role in frisson. Sachs uses different songs in his lectures to see if students get it.
I'll say raise your hand when you get a chill, and I'll play a piece of music, a classical piece, and maybe half the people will get it.
But then he plays this. The Rolling Stones, Give Me Shelter.
Have you ever seen the movie 20 Feet from Stardom? The
Oh, about
documentary?
backup singers.
Yeah. There's a part where they isolate the vocals from Give Me Shelter. And I play that, and 90% of the people experience chills, sort of independent of where I go.
I have to tell you, bringing that up made me think about it, and I got that little kind of thing at the back of my neck.
But why would that happen?
The high-pitched notes that she hit almost sounds like a scream, and it's very important ancestrally for us to be able to pay attention to a scream, figure out what's going on, and either run or fight, whatever we need to do.
So how come that manifests as pleasure? Well, it's because our prefrontal cortex, the more rational thinking part of the brain, kicks in.
So you realize very quickly after you have this really quick startle reflex that there's nothing actually threatening about the piece of music, that you're sitting in a safe space with your headphones on, and it's in that reappraisal that we tend to think of the pleasurable response as emerging.
And whether you find listening to music so pleasurable you get chills, or you absolutely despise a song, it can produce absolutely fascinating effects in the brain. According to Levitin, music we enjoy triggers the brain's internal opioid system. Yes, opioid system. And just like the opioids that come in pill form, these chemicals make you feel good and help relieve pain. And music you don't like? Well, that releases cortisol, the notorious stress hormone. But that's not even the half of what music can do in the brain.
You turn on the light. Mary.
When former Congresswoman Gabrielle Giffords was shot in 2011, the left side of her brain was severely damaged, leaving her struggling to speak, a condition called aphasia.
Gabby, are you frustrated?
But to get an idea of just how powerful music's effect on the brain can be, watch this video.
You ready? This little light of mine, I'm gonna set it.
That word that she had been struggling to say, light, came easily in song.
Why would she be able to sing a word when she's unable to say it?
What we know about the brain is that the left hemisphere controls language, and there are many other parts of the brain that have music access.
Music therapist Megan Morrow's job is to help patients use those other pathways to regain language.
Sometimes I compare it to being in traffic and you can't move any further, but you might need to exit and take a feeder road to get you to your destination. So music is basically like that feeder road to the new destination.
Like a detour. So we know that music can help us relearn things like speech by accessing alternative pathways in the brain, and that learning to play music can help strengthen brain connections. But what about making music?
So for me, music is like, it's the language of humanity. No matter where I go in the world, no matter, man, if I'm playing something, it doesn't matter if someone can't speak the language and they're into it, they're into it.
This is Xavier DeFrepoles, better known as Fantastic Negrito. We brought him to UCSF to meet Charles Lim, a neuroscientist who studies musical creativity.
The Duffler's up next.
To understand how Fantastic Negrito's brain works when he's making music, Dr. Lim had him play one of his songs while going through the fMRI. So how did his brain respond? The areas that process sensory and motor skills, along with sounds, lit up. You can see them here in red and yellow. Makes sense, right? But here's the really interesting part. Lim asked him to improvise to see what happens when he's creating something totally original.
It's like Star Wars in my head. It's like Star Wars in my head. I don't like this crazy sound. Makes me feel like I can't get down. Stop.
Now watch what happens to his brain. The areas that were active before, the ones that deal with motor skills and sounds, are even more active. But see how there's way more blue in the front of his brain? That's the prefrontal cortex, and it's associated with effortful planning and conscious self-monitoring. And it's blue because it's less active.
We see that the prefrontal cortex appears to be really shutting down in these moments of high creativity, kind of like letting go of these conscious self-censoring or self-monitoring areas that normally are there to help control our output.
And Lim says it's about more than just letting go.
You view it from the perspective of survival. If human beings only could do memorized rote responses, we'd be long gone. And it's not just the thing that happens in clubs and in jazz bars. It's actually maybe the most fundamental form of what it means to be human, to come up with a new idea.
Travel, and we travel, trying to find.
So, music is so much more than notes on a page. It can change the way we think and speak and feel. But is there a limit to what science can tell us about music?
Just when I discover the answer to one thing, 5 new questions pop up that are more interesting than the first, and I've gained an appreciation for how complex the music making and music listening system is. It's not demystified for me at all. It's more mysterious than ever.
La la la, la la la, la 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 la.